Talk will be by Kotecky from Warwick and Praha, and he will talk about cluster expansion and historical overview.
Okay, so this was, I should apologize because I was somehow cornered into this topic somehow.
And you won't say by whom.
Yeah. and actually, somehow it will not be that much historical overview. What is my plan is indeed to show you, so it will be very simple, it will be really trivial somehow, so especially for mathematical physicists here, it's really somehow, you should leave immediately because there is nothing for you to learn. But somehow the idea would be to show how this polymer models or polymer graphs, how they are occurring and what we are doing with them and how we are employing this cluster expansion theorem. And then at the end, maybe I will somehow quickly go through some steps in this. There are essentially with this cluster expansion, there is this, as Alan already mentioned, there is this thing that everybody hated it first. Somehow the idea of this is complicated. I don't want to hear about that. And then everybody invented his own method how to deal with the thing. So there is so somehow through the history nobody was reading the things that were written before, but everybody was inventing new methods. So somehow there is quite a turmoil, quite a chaos. But somehow slowly it is improving and things are again taken to the new approaches and things like that. So I will somehow mention some very old things, but I see somehow masters of this. I mean, Salvador is sitting there, who somehow was one of who started all this. So somehow I am certainly not the guy who should somehow try to explain very much, the really historical roots of this. I was in kindergarten where all this started. Okay, so first I will start by reformulating this, say Dobrushin theorem. So somehow I tried to keep the notation of Alan without knowing what it will be exactly, so I was somehow not. But okay, I tried to do my best. So we have the graph, we have some vertices, and we have edges of this graph, and we have some weights on the vertices of the graph. So we have this W is, you were denoting it as a vector W, so it is a collection of complex numbers, one for each vertex of my graph, okay? Then for every y, so here is the first difference, you somehow, from some reason, you called lambda subset of x. So of course subset of x is y. So for any y, which is, this x is you will see it can be an enormous graph. It is a graph that has, countably many vertices, but from every vertex there is countably many edges, so it's really an enormous graph. But for every finite subset of this graph, you can define this, what we call partition function. So partition function is the sum. Okay, I should say I am in the level 3 language of what Alan was describing, and I will stick to this level 3 language because I want to illustrate, and this is the simplest thing to do somehow. So this partition function is simply a polynomial. It is sum over independent sets, subsets of this y, and then product over x's in this independent set of wx's. Okay? Now comes the cluster expansion theorem. Essentially, it is the version given by Dobrushin. I will somehow, maybe at the very end, I will somehow give some remarks what is somehow where it really differs. And it is slightly rewritten already here. I somehow changed the notation a bit because I didn't like terribly much the notation Alan has. So okay, so we have this multi-indices. So the claim is there exists this coefficient, this Meyer coefficient. So Meyer coefficient is a function on multi-indices. So n is multi-index. I do not put this arrow there, but n is multi-index. So this kernel X is the set of all possible multi-indices on my set X. Okay. So I have multi-indices. I have the real numbers Cn corresponding to every possible multi-index, such that whenever W satisfies the following conditions, so this is slightly different condition from what Alan was saying. It's equivalent, of course, but it's written in different language. So whenever W is such that absolute value of Wx, for every x, the following should be true. Absolute value of Wx is smaller or equal than Rx times product over all neighbors of x, all y's that are neighbors of x, of 1 minus Ry, okay? Where R is a function going from the vertices of our graph to the interval 0, 1, excluding 1, okay? So this is some sort of condition of smallness of W. So whenever W are that small, this is some sort, if you think about it, is a polydisk. So somehow for every x, I define the size of my, how big Wx can be. Then the two conditions are true. Then for every y subset of x finite, zy of W differs from 0, okay? And hence we have, this is just the Taylor expansion of logarithm z, okay? So this coefficient, so somehow important thing is that the coefficients, they do not depend on Wy. That these are just some numbers, okay? They depend on this multi-index, and we have sum over all multi-indices with support in y. Okay, so multi-indices on y. Okay, so this is the first condition. So this is what we call cluster expansion. Expression of logarithm z in this way, as an explicit sum of explicit terms somehow. Okay, yes?
For any, there exists C such that
whenever W satisfies this for some R, then this is true.
But C already given.
C is given once forever. There exists such C.
But you can be more explicit if you want.
Such that for every W that satisfies this is true, for example. Z differs from 0, and this is true.
But sorry,
Yeah?
you're forgetting there an epsilon, cardinality of y.
Where?
In the last formula. 1 over cardinality of psi log.
No. This is the formula.
But if you want, you can be more explicit. Right?
Maybe you might, maybe you want n factorial here, but somehow I included this into Cn. But otherwise, it's correct formula.
But if you want, you could be more explicit and say that the Cn's are exactly the Mayer coefficient Cn that I defined.
Yeah, okay. Whatever, there is explicit formula for them, but for me...
My expansion is the same thing.
Yeah. Okay, but always there is a second condition, and second condition tells me something about convergence of this series that is here. Here I take sum over all multi-indices everywhere. So, already this sum is infinite because I have all possible multi-indices, so it's infinite sum. But here it is somehow doubly infinite because I have infinitely many multi-indices, but moreover, it is on huge set. These are all multi-indices on this x over there, so it is on all my vertices, so they can be as large as possible.
Right. So your x is countably infinite, whereas I would work separately on each finite.
Yeah, exactly. And okay, I have the condition that support of n, so n is non-zero on a given vertex x. Okay, so I sum over those that are non-zero on a fixed given vertex x. Okay, and the claim is that for every x, this thing is bounded by actually something in terms of this R that was in my condition over there. Okay.
Any tonicity in y? If you have y prime one within the other, the coefficients are only growing.
Coefficients are the same. Coefficients, they do not depend on y.
The summation takes us.
Yeah? Only the summation depends on y. So this is important. Cn's are given once forever. These are, coefficients for all the words somehow, so to say. And now, in a smaller volume, I sum over some coefficients. In a bigger volume, I sum over some bigger set of coefficients, but the same coefficients with the same terms somehow. Okay, so in this sense, it is the monotonicity you're asking for. Yes?
The theorem should we erase the first line? If W satisfies, then Z is not zero and has expansion, and then
No, I wanted to stress that the C somehow do not depend on W or whatever. So I really want to say there exists C independently of W, such that this is true. Yeah? Independently of W, independent of Y. Okay, these are, once forever given set of coefficients. These are exactly the Meyer coefficients. And there is explicit formula for them, as Alan was showing you.
But they depend on the graph, right?
Yes. Yes. Okay. Okay, so this is the theorem. Maybe let me copy here the condition, the condition star, because we are going to use it, verify it. So the condition was Wx is smaller or equal than Rx, product over Y belonging to neighborhood of X, 1 minus R of Y. Okay?
And it's equivalent to the Debruchin condition in the form that
Yes.
we gave it by a simple
Yes,
change of variable.
yes, just, by a funny change of variable, because you somehow R,
Little r is 1 minus.
K times W is R or something like that, so it's,
Is there an intuitive reason why this is called a cluster expansion?
Well, yes, it is somehow, it is very easy to show that the CNs are 0 whenever support of N is not connected. So it means,
To the proof of
so it means it is a
Meyer-
connected chunk of the graph somehow. It's living on a connected chunk of the graph. Yeah? Okay, so this was the theorem. And now I want to show you how we are using this theorem, how this, how these expansions arise in physics. So, okay. This is, all my talk will be just, somehow talking around, cluster expansion here and there to give some more information, because, during the week there will be a lot of information, so to have some background. Okay, so the simplest model we have is the Ising model. And here is partition function of Ising model. So it has not, up to now, it has nothing to do with my model described before, because now I have a chunk of lattice. This is this lambda. It's not Alan's lambda. Okay, so it's a lambda. It's a chunk of lattice. Okay, here. At every vertex of this lattice, I have variable sigma I that takes value plus minus 1. Okay. Whenever I have set of variables on this lambda, of this sigma, so I call all the set of them on lambda, I call it sigma lambda. So whenever I have this sigma lambda, I can write this expression over there, e to beta sum, this funny symbol ij. These are nearest neighbors in my lattice, so these are pairs of I and j that are somehow nearest neighbors connected by an edge in the lattice. So I have sum over I and j such that they are connected by an edge, sigma I, sigma j, plus beta h, sum of sigma I. There should be I belonging, all i's and j's belong to lambda. Okay? So this is just standard partition function of Ising model. Physicists are interested in that, and a lot of knowledge we are getting is just looking carefully on things like that. Okay, and I would like to do something that is called high temperature expansion of this partition function. Okay, so what is this high temperature expansion? Okay, I should point here. So what I do, instead of those sums, I write products. Okay, now I have sum over, I should stress, there was sum over all sigma lambda, so it is sum over 2 to lambda configurations of these sigmas. Okay, independently I choose in every vertex plus 1, minus 1, all possible possibilities I have there, sum over all those sigma lambdas. Then I have product over these edges, e to beta sigma I, sigma j, and then I have product over vertices in lambda, e to beta h sigma I. Okay, now I will rewrite this e to beta. Notice that this sigma I, sigma j is also always either plus 1 or minus 1. So it is true that e to beta and something that is plus or minus 1 simply equals cosh beta plus sigma I sigma j sinh beta. Okay? You just have to check, but there are only two possible values of this function and two possible values of this function, so you check that they are really the same. Okay? I can do the same for this guy here. So it will be cosh beta h plus sigma I sinh beta h. Now I can take out this cosh beta h outside of everything, and the same with sinh. So I will have 1 plus something sigma I sigma j tanh beta here, and I will have 1 plus sigma I tanh beta h. So I will get a formula that looks like that. Okay? I have some prefactors that are somehow just some fixed number in terms of lambda, and then I have sum over sigma lambdas, product over I and j, 1 plus sigma I sigma j tanh beta, product over I, 1 plus sigma I tanh beta h. Okay? Now I will somehow expand these products. Okay? So how I am going to expand them? I will simply do the following thing. The first product is over edges. Okay? So I take sum over all possible collections of edges. These are these gammas. Okay? Collections of edges. And the second product is product over sides, over vertices of my lattice. So I will have sum over all possible subsets. V are subsets of lambda. Okay, so this sum here is sum over all possible collections. Sum over all possible collections of edges in this lattice. Okay, and then I have also sum over all possible subsets of lambda. Okay. Then I have tanh beta to the number of edges, tanh beta h to the number of sides in my V, and then I have product over edges ij in this gamma of sigma I sigma j, and product over I in V of sigma I. Okay. Okay, now I have just two sums, so I would like to exchange these two sums. I have sum over gamma and V and sum over sigma lambda, and if I try to exchange them, so this is pictorial description of the set gamma V. So I have some collections of edges and some collections of vertices. Okay? And now this sum over sigma lambda for a given collection, for a given gamma V, will very often be 0. For example, for this case, it will be 0. Because if you carefully look on this graph here, so you have, okay, this vertex is of even order, is of order 4. But say this vertex is of order 3. So if you collect all possible sigmas that will come with this vertex, you will get sigma to the third power, so it will be sigma. So if I keep this sigma fixed and resum over all other sigmas, so whatever will be the result, it will be some number multiplied by this sigma here. And now at the end I sum over this sigma, but it takes values plus and minus 1, so it will give me 0. So whenever in this graph here there is a vertex of odd order, like this one or that one here, okay, then I am getting 0. So the only terms that are not giving me 0, they look like that. Okay? So these are the terms where I have some graph of these edges, and whenever there would be dangerous vertex that would be odd, I add to this vertex the set V. Okay? So it is the set of graphs that are giving me non-zero value, actually the value 2 to lambda then, because then this product is giving me 1. It's simply 1. It's product over sigmas over even number of sigmas in every vertex, so it is giving me 1. And then I sum this 1 over all possible configurations. There is 2 to lambda of them, so I have 2 to lambda if simply odd vertices of my graph gamma are exactly the set V, this set V. Okay? So I can forget about gamma and V, and I can simply write it as a sum over all possible collections of subgraphs gamma, and then I will somehow remember that whenever I have odd vertex, there is actually this factor coming in odd vertices. Okay? So I hope I summarize it here. So my Ising model partition function in this expansion is something, so up to this, constant factors here, is sum over all subgraphs of my lattice. Okay? Okay, now I change notation, sorry. So this is just, this is just a glitch. I divided this subgraph of my lattice, I divided it into connected components. And I call this connected component small gamma. So I am thinking about this capital gamma as actually collection of connected components. So I have, one piece here, something like that, another piece here, another piece here. And this I call gamma, gamma 1, gamma 2, gamma 3, and gamma is collection of those. Okay? So I have sum over collections of small gammas, product over small gammas in this capital gamma, and for every small gamma I have the weight which is tangents hyperbolicus beta to the number of edges in gamma, and tangents hyperbolicus beta h to the number of odd vertices of gamma. Okay? But it starts to look exactly as something we had in the abstract polymer model before. Because we had sum of independent sets, okay, and then we had product over gamma. Okay, so if I declare that my vertices of my abstract graph, of my huge graph, so the vertices of my abstract graph will be these pictures here. Will be what I call polymers. So these are vertices of my. So now I'm constructing the graph G equals XV. XE. Okay? So its vertices will be things like that. And I will consider distinct vertices. If I take this animal here and I shift it to some other position, this will be another vertex. Okay? So these are my vertices.
So the vertices are connected subgraphs
of
the original.
Of the original lattice.
Not
okay?
vertex sets of connected subgraphs. It's the whole picture with the vertices.
Yeah, just connected subgraphs of this. Okay? So these are my vertices. And now I say that, and what are the edges? The edges are simply pair of vertices that intersect. So for example, if I have this vertex here and this vertex here, so they touch, they intersect, and then I draw an edge between those two. Okay? So if I have gamma 1 like that and gamma 2 like that, and now they are in such position that they are touching, that I draw in this abstract graph, I draw an edge between them. And then this sum is exactly what we had before, because we have sum over collections of vertices. I mean, here we have sum over all connected components that are disjoint by definition. Okay? So in our new language, these are vertices that are not connected by an edge. So in our new language, these are independent sets of vertices. And then I have product over the vertices in my independent set, and some weight factor. This is some complicated weight factor. Okay? So this is our Wx of gamma.
So there's no interaction between pairs of vertices yet in this.
Well, this is level 3, so there will no be.
Oh, that's right.
Yeah, this is level 3. So the only interaction is this, whether they are connected by an edge or not. Okay, there is hardcore interaction stemming from this condition. Okay.
The weight function is the last factor, right? You said the weight function is the last factor.
Yeah. So all this is the weight function. So if you wish, we can. So this gamma was what I was denoting independent set before. Okay, so it's independent set, which is a subset of my set of my huge set of vertices, all possible polymers. Okay, and for every x in my huge set of vertices, I have the weight Wx, which is simply tangens hyperbolicus beta to the length of gamma. I mean, x and gamma is the same thing. And tangens hyperbolicus beta h to the power v odd of gamma. Okay? Okay.
Positive.
Pardon?
Beta is positive. What's the sign of beta?
Beta, well, in physics it's positive, but you can think about beta, which is complex, actually. I prefer to think about beta because our weights in the abstract model, they can be complex. And for studying convergence, it's useful to think about these things as complex variables somehow. Yeah? So think about beta as complex if you wish. Okay? Okay, so now we are in our situation and we would like to use our theorem. And we had this condition in our theorem. Okay? So let me show you how to check this condition. Let me see whether I am really doing it. Okay, so let me show you first how I am going to use the claim of the theorem. Okay? So I'm still going in the direction of identification because lambda was the set in my lattice. But for every lambda, I can consider the set of all polymers that are living in lambda. Okay, as it was in this picture. All possible polymers living in this lambda. Let me call it y lambda. Okay? Then this thing actually turns out to be exactly, and the weight, as I said, is exactly this thing. And then we have simply z of y lambda of this w here, is exactly, so it is given by this formula, but it is exactly our definitoric formula for our abstract polymer model, or how to call it. Okay? Okay, and now I would like to use, so now we have a claim saying something about logarithm of zy.
So you drop the prefactors, right?
Yeah, prefactors are just, they are explicitly computable. You can somehow, pardon?
Polymer is the same as connected subgraph.
Yeah.
Connected but not spanning.
Not spanning.
No, not spanning. Yeah. Okay, but there is still not connected. Gamma is not connected subgraph. Gamma is just union of connected pieces. Okay. Okay, but we will come to cluster expansion. But first we have to verify the condition star. Okay. So first of all, what was our W? W was, okay, tanh beta to the number of vertices, to the number of edges, and tanh beta h to the number of some vertices. So, okay, tanh beta is smaller than 1, so I can forget about this one. And this thing will be somehow epsilon to the number of edges. Okay, if beta is somehow small, so this thing is epsilon to the number of edges. So I would like to be able to verify our condition in a situation where I know that W gamma is smaller than epsilon to the number of edges. Okay? So what I will do, the following thing. So first of all, there is some geometric assumption that is included. And the geometric assumption is somehow, so assume that epsilon is so small that the sum of connected graphs containing a given vertex is smaller of this number of e times epsilon to the number of edges is smaller than 1. Okay? So of course by taking epsilon small enough it's always possible because somehow number of graphs on my square lattice or cubic lattice or something like that. So this number of graphs is somehow polynomially bounded of a given size. Okay? So you can somehow write your not polynomial. It's exponentially bounded by with a fixed exponential somehow. Okay, so I can always choose epsilon so small that I will kill this number and I will get this thing here. So I'm not going into that. This is a simple somehow exercise. Okay, so let me assume that I have chosen epsilon so small that this is true, and then what I can do, then I have to choose my R. Okay, so first of all, you see. I am somehow closer to physics because I use this incompatible. So gamma prime incompatible with gamma, these are these guys that intersect, it's exactly the edge of the graph, okay? So I have some, so then the following claim is true. once this is true, it is true that sum over gamma prime incompatible with gamma can be bounded by sum over vertices included in gamma, okay, and sum over gamma prime containing a given vertex, because the only incompatibility is that they intersect in some vertex, okay? And since this sum is smaller than 1, so this is smaller than length of gamma, okay? So this is easy conclusion from here, and using this, now we choose for R gamma, for this R gamma here, we choose this funny number, 1 minus e to minus e epsilon to the power gamma. Okay? So let me simply take this choice and let me verify that this condition is satisfied. Okay? So what I do now, so I want to prove, so this is the condition, R gamma times the product over 1 minus R gamma to the number of neighbors, over neighbors, product over gamma prime that are neighbors of gamma, which is exactly this thing here. It is, 1 minus R gamma, so this 1 will disappear, and I will have this E. I have product over this E, so it is E to minus sum over gamma prime that are neighbors of gamma of this factor here, E epsilon to the power gamma. Okay? And I would like to show that this ugly product here is bigger or equal than epsilon to the power gamma. Yeah? This is my W gamma. I know that W gamma is smaller than epsilon to gamma. This was my assumption, so I would like to show that it satisfies the condition. Okay? So let me start from this and let me show some lower bounds. Okay? So just multiplying here by e to E epsilon gamma and dividing, I have e to E epsilon times gamma minus 1. Okay, I just multiplied by it, and here I divided. So I added this term here. I added the term e to E epsilon to gamma, which amounts to having not only sum over gamma prime that are neighbors of gamma, but they are in the extended neighborhood, including gamma itself. Okay, so I have this, and now I do some simple bounds. So first of all, I use the fact that e to x minus 1 is bigger or equal than x, so I can bound this by this, okay? And for this, I use this thing, okay? I know that all this sum is smaller than gamma, so e to minus this sum is bigger than e to minus gamma. There should be number of edges in gamma. And then I have e to gamma, e to minus gamma. This will cancel, and I will have epsilon to the power gamma. Okay? So this is how you verify the somehow abstract condition that sounds very unintuitively for very simple intuitive case. Whenever you have, you have something, and as Alan was describing, something that is decaying very quickly with the size of my gamma. Gamma has a size. Gamma is a vertex of my abstract graph, but also I can think about this as my polymer, and this polymer is geometrical object with some size, and our weight of the polymers is always such that their weight somehow is decaying very quickly with the size of polymer. Okay, so every vertex in my abstract graph has a lot of neighbors, but somehow new neighbors that are coming are bigger and bigger, because if you have one vertex here, something like that, and now you list all its neighbors, so all its neighbors are all the somehow polymers that are intersecting it, and they must be bigger and bigger if I am going one by one over them. Okay, so this means that this product somehow is somehow you can do something with that. This is the only reason for this. This is what is coming here. Yeah?
The assumption at the beginning is your condition with the Kotecky price condition with a equal 1.
No, our condition is somehow hidden here by somehow. Our condition would be if you do not if you use this from the very beginning. If you replace e to x minus 1 by x.
If you write instead of e to the a, and then less or equal.
Well, somehow it is, but okay, let me not go into this because I really want to verify it in the simplest possible case where I have epsilon to gamma, not something
Because I'm saying this
stronger.
because you are proving by this assumption that the polymer gas converges, and this assumption here is in fact the Kotecky.
Yeah. This is this is why our condition was somehow. I will explain why you shouldn't say Kotecky price condition, but this I will come to it. Okay. Yes.
Can I make a remark on the Kotecky price condition?
Yeah.
I mean, this condition you have there, it looks extremely, out of nowhere. W sub x less or equal to r sub x times.
Yeah. But it comes exactly in your inductive proof. It comes, in the proof Alan was showing. It comes exactly in the point where you need it. It comes in this form. So this is why.
Not the Kotecky price.
This is not Kotecky. This is Dobrushin.
I understand the difference. But actually, if you look at that equation, you can rewrite it as a fixed point equation for a certain combinatorial species. And then when you look at it from that point of view, it's a species of rooted, slightly enriched rooted trees. And the enrichment is to go from Kotecky price to Dobrushin.
Well,
and
somehow, we should ask Bill to give a talk because he has this beautiful paper. It's really beautiful somehow.
Can you do
And-
it without help algebra?
Okay, good.
Yeah. and if we should ask him because otherwise, in every talk he will interrupt us.
We'll save time.
and so it will save time, and in addition, it's beautiful. It's really very nice.
Bill, can you prepare a talk by 4 o'clock on Friday?
Sure.
Okay, you're on.
Yeah. Okay. So
sorry, this way I will
sorry for forcing you into that, but
popularity.
this is with that you pay for asking too many questions. Okay. So what I'm saying here, let me go back. So we verified assumption of cluster expansion. Now I want to use it.
Go back
Okay.
a second.
Yeah.
Go back to you had a condition that says assume.
Yeah.
Go,
Back.
yeah.
This will be difficult because somehow.
There we go.
Yeah.
The thing that you're assuming can also be verified, for example, in terms of the maximum degree of the underlying graph lambda.
Yeah. You can do it modularly. I agree with that. Yeah. Somehow, surely. Yeah. You can verify just for one edge that it is more, and then you somehow. Then you plug it into your species machinery and.
In here, there's a little lemma of counting connected subgraphs containing a given point
Yeah.
and having a given number of edges, which can be done in terms of maximum degree of the underlying.
Yeah. Sure. Okay. So we have at our disposal the cluster expansion theorem for this particular case. For this particular case, with the weights like that, and with the polymers that are exactly this, these animals, these graphs living on, these little graphs living on my lattice. Okay. And now I would like to use it. So one usage is that what physicists are interested in, I was computing this logarithm I was computing partition function in a finite volume, in finite lambda, okay? But what physicists are interested, they are interested in this thermodynamic limit. So it is a limit with lambda going to infinity of 1 over lambda logarithm z. So essentially the claim is that logarithm z is essentially additive, and you can divide by lambda, you can compute the limit, and it gives some number. Okay, so the limit exists. So it's easy to prove that the limit exists. But what you have here by cluster expansion, you have an explicit formula. And this is the explicit formula we can easily prove. Okay? So to explain the explicit, so we understand what is Cn, we understand what is W to the power n. These are these multi-indices. We do not understand what are this Vn here, so let me explain that. So whenever I have I have my little graph gamma here. V gamma will be simply number of vertices of this thing. Okay, number of vertices of this vertex of my abstract graph. Not number, the set of vertices. The set of vertices of this polymer. So this is V gamma, and then Vn is simply union of all V gammas of all gamma that are in support of my. There should be n here instead of x. This is my. I am used to call n to call x. So this was somehow slipped. So there is support of n, and support of n is all gammas for which n gamma is non-zero. Okay, so this is Vn, and then I am somehow claiming that this limit is explicitly this number here. It is sum over all n's such that Vn contains a given point, for example, origin. Also, I am supposing here, which is true in this model, that the weight of these gammas do not depend on the position of the gamma. If I shift it to some other position, it will have exactly the same weight. Okay? Of course, it depends on the type of gamma, how it looks like, whether it's big or small. But it doesn't depend on position on my lattice. Okay?
So that up to this slide, lambda was an arbitrary graph without...
Sure. It was totally...
So it's now that you're asking some transitiveness of the graph.
Yeah. Up to now, it was totally, yeah. Sure. And this is clear why I somehow need it at this position, because I'm somehow looking for this limit. And of course, if it would be widely depending on the position, then this limit cannot exist. But by somehow, it would be different in different places. And you can imagine that you can easily construct models or situations where this limit wouldn't exist, and it would be somehow. So.
But average of a starting position instead of taking 0 would maybe exist.
Yeah, this would. Yeah. Actually, my proof now will show somehow. Probably here you should then write some sort of average over these points, but I do not know how to do it because average over zeros in different positions. But there are infinitely many positions. Yeah, so it's somehow. Yeah, but maybe some Cesaro sum or sum or something like that. I can imagine that something can be done here. Okay, so we understand the formula. Now let me prove it for you. Okay, so what I will do, I will multiply. Forget about the limit. I multiply this by lambda, so I have logarithm of zy of lambda. Okay. I multiply this by lambda, and I compute the difference. Okay? But for logarithm z, we have our cluster expansion formula, which was exactly this. This was sum over multi-indices such that they were living in y of lambda, but living in y of lambda means that they were somehow multi-indices on contours that were living in lambda. So it means that Vn is subset of lambda. Okay, so I have sum over n's such that Vn is subset of lambda, Cn w to the power n, minus, and here I just wrote this sum, but I wrote this sum multiplied by lambda. I multiplied left and right hand side by lambda, and I multiplied it by funny way. I simply, instead of writing lambda times this, where Vn contains origin, I wrote sum over I in lambda, sum over n, where Vn contains I. Okay? It's translation invariant, so I simply wrote this sum lambda times. Okay, this sum is always the same for any I because there is no volume here. You see, these Vn's are as large as you wish. There is no restriction on the volume. Here there is sum over all possible Vn's, all possible multi-indices. Okay. Okay. So now I would like to exchange these two sums in this term here. So what I will do, simply putting this sum first, I have sum over all possible n's, and then I have for every fixed n, I have sum over I in lambda, but also over I such that it is contained in Vn. So it will be Vn intersection of lambda, the number of points in that. Then I have this divided by Vn that was in my formula, and then I have Cn w to the power n. Okay? So I have the difference of these two terms, of this term and this term. Okay? Now if you look carefully on this, whenever n is such that Vn is subset of lambda, then this thing is exactly what, then Vn intersection lambda is simply Vn, this ratio is 1, and these two terms cancel. Okay? So the difference of these two sums actually is what is written here in this absolute value. Okay? It is minus sum over n's such that they are not contained in lambda, so they are sticking out, so intersection Vn intersects lambda complement. Okay? And then you have what you have here, Vn intersection lambda, Vn, Cn, Wn. Okay? Now I want to estimate absolute value of this. This will be my remnant term. But notice up to now, it was exactly equality. So this is exactly the difference of this, of logarithm z and n times my limiting, or lambda times the limiting thing. Okay? So this is exactly this thing, what I have here. Okay, so what I can do, I can notice that first of all this Vn is connected. This is my, somehow, because this is this cluster property that support of this, this multi-indices that are non-zero. The Cn, I didn't prove it, but it's really, believe me, it's very easy to prove. The Cn differs from 0 only if, somehow, if I draw all possible gammas in support of n, they will somehow organize into a connected structure. Okay, which means exactly the same. So Cn differing from 0 means that Vn is connected. Okay, so Vn is connected, and it somehow reaches out of lambda, and in the same time it must reach inside of lambda, because otherwise this would be 0 here. Vn intersection of lambda is 0 if it doesn't reach inside. So it means I have my lambda here, my set. So it means that this n somehow pictorially, which is something like that, must go from inside to outside. So it must intersect some point in the boundary, on the boundary. Okay. So I can bound this absolute value by sum over the points on the boundary. Come on. Sum of the points on the boundary, and then sum over n's whose Vn contains a given point of okay, I bound this by 1, so just absolute value of this. Okay? But this was essentially with slight grinding, it's not really somehow, it's not really, but it was essentially the condition, the second condition of cluster expansion, the bound on this thing.
Why is it not really?
Because this is Vn containing I, but I is in this lattice, not my original. So yeah. But we had condition. If you think about some sort of elementary graph, like a square like that, and now you can think about we have sum over all those that intersect this given square. Yeah. And intersecting given square is essentially the same as just intersecting one point.
Well, even if,
4 times more.
Even a single vertex is a polymer.
No. No. Because it's odd. It gives 0. I mean, polymers are really edges,
If you
collections of edges. Single
No,
vertex is not a polymer.
No, because it would, for example, if you had non-zero magnetic field, it would have weight tangent, hyperbolic.
Yeah, but
tangent.
it gives 0 in the sum.
It's not a area.
It's even. It's odd, sorry.
No, but
It's odd, and you cannot repair it by, I really constructed my graphs by taking edges and then saying, okay, whenever I have odd vertex, I add this V there. I add tangents, hyperbole, tangents, beta edge. Pardon?
One edge is okay.
One edge is okay. This is the smallest. Okay, one edge. And one edge is just 2 vertices somehow, so so twice as much or something like that. But it's possible to do actually. How I was verifying the condition, I was already using this condition that sum over all graphs that somehow intersected a given point was smaller than something. And this is exactly what you somehow, okay? Okay.
Hidden in the
Yeah,
prefactor.
it's hidden there, but it's somehow, so this thing is bounded, and then I have, you know, number of points in the boundary times some constant, this is the constant here, times the number of points in the boundary, and this is, you know, the difference of these two terms multiplied by lambda. Now if I divide by lambda, so I have here divided by lambda, with lambda going to infinity, it goes to 0. Okay? So I see exactly that this limit, you know, it's very powerful statement, because I am somehow saying, okay, this limiting thing, some sort of something constructed by limits, is actually exactly this sum. So for example, this limiting thing is analytic in whatever W is analytic in. Yes, W is analytic in beta, for example, here, or in H. So I immediately know that free energy, this is essentially free energy, is analytic in beta and H for high temperatures, because, you know, my condition was that beta was sufficiently small, which is high temperature. Okay, how much time I have?
Nothing that one can do.
Pardon?
3-4 minutes.
Okay, so let me now very quickly go through the history of cluster expansion. Okay, there is also low temperature. So
7 minutes.
7 minutes. Okay, so let me go very quickly through the history. So somehow it all started when I was in kindergarten, and somehow my understanding was there was the famous Oliver Penrose who had a proof of some sort of cluster expansion, and he was thinking it's so stupid thing that it is not worth of publishing. I mean, Salvador will verify whether I'm saying
He thought
whether
that
it is.
theoretical physicists would not care.
Yeah. So he is not going to. But then this guy Grunwald published this paper, and only after that he decided, okay, after all, my proof is slightly different, so let me publish my proof. So then Oliver published this proof. Okay, and notice somewhere in the text there are the word. You see it here. There are the word Kirchhoff-Salzburg equation, Kirchhoff-Salzburg integral. So this was somehow the popular way of doing these proofs that time. Okay, until quite some time after that, there was, you know, say David Riel had something. Again, you see 63, still kindergarten. Well, this is already gymnasium. Okay, then you have this thing. Then you have important paper, you know, couple of papers that were really using, you know, this Kirchhoff-Salzburg equation in a very somehow important way, and this was, you know, Salvador with Galavotti. So they had about 3 papers or something like that, and this all happened, you know, while they were on barricades, essentially. I mean, not here, but, you know, sometime after that. So these were the years. I was also actually in the fall of '67. I was in the anti-communist demonstration in Prague. So this was somehow. So we were also on barricades. There was the famous student, and, you know, important paper were Gruber-Kunz. Again, you see somehow. Oh, it's not written here, but somehow actually I have. Till this morning, I somehow remember there is this, you know, I should say something about this Kirchhoff-Salzburg equations. I will not, because it's really in 6 minutes I will not succeed. But somehow, till this morning, I somehow knew. I was looking through this paper, and everything is somehow so complicated, and there is no clean, nice way. And I remember there was somewhere nice, clean way. This morning I went to the library there and looked in the Sinai book, and indeed in Sinai book there is a very nice, succinct, you know, somehow way of writing. These are, you know, Meyer-Montrol equations, but who cares? Then there was important paper by Camarota, and so this is the copy of the page from Sinai book, but I am going to skip this. These are the equations somehow. My idea was somehow to, while you are watching, to somehow translate the equations for you. Forget about that. Okay, this is our paper, and I just want to make 2 comments about this, you know, somehow. So there was our paper and there was Dobrushin paper, And both of them have somehow, Dobrushin paper is beautiful, but it also has some disadvantage, and our paper has, very big disadvantage. So first let me mention our disadvantage. Somehow it was, the idea was that, we want this equation, we want to write logarithm of z as a sum of some terms, okay? But of course by Möbius inversion you can always do that. You simply define these terms as sum over minus 1 to the number of elements of this logarithm, okay? So this is tautology, okay? And the only thing you have to prove is the nice decay. And this you do by induction, okay? So this was our idea, for us important thing was we have this somehow induction. And there is this condition, this is what you call our condition somehow, okay? And there is a big disadvantage here, is that somehow there is very unclean connection. These terms here, they are defined in terms of this Möbius formula using all these preceding logarithms, so to say. So they, in our expansion, in the expansion you were showing in Dobrushin expansion, you have Cn w to the power n. So it very clearly depends on this w. Here it depends on w's, but somehow in a complicated way. And if you are interested, for example, in some dependence on beta, or, on some terms that is sitting in w, so it's difficult to compute derivatives with respect to this term. It's difficult to see dependence on some terms that are sitting inside of your weights. But this is very difficult here. While in the older version, it was very explicit. And the newer version in Dobrushin, it was also very explicit.
But it's very easy, as I showed, to get the Mayer expansion.
Yeah. Sure. So let me now make an important comment somehow, because I'm somehow we clearly state in these are lines from our paper, and somehow there is this condition. There was this condition, and somehow people are calling it KP condition or something like that. But it's not really fair. Because there was a paper by Guerra that was somehow, I was unable to find it because it's not a paper, it's lecture notes and I do not have them. But somehow, this is what we wrote, assumptions of type, so this is our assumption, were used by Guerra, so of this type, but certainly in slightly stronger form. But certainly, then there was this student of David, Jiří Navrátil, who in his diploma thesis used this Kirchhoff-Salzburg equation machinery, and he simply proved the theorem in exactly the same way as we have it. Okay, so in this, well, not exactly, because he was in exactly the same way you would prove it by standard method, so to say, not using this Möbius formula. Okay, so this is somehow, so the condition certainly. So first of all, it was before by Navrátil. We are somehow clearly. Unfortunately, this Navrátil then disappeared. He made his, he even was not doing PhD. This was very, Miloš remembers him, this was very funny student because he was never saying anything. He was just sitting in the seminar. And then, after many seminars, he would say, I have the proof of this. And then he presented something, really somehow unbelievable. But then he again for half semester didn't say anything. So, and then he disappeared simply. Okay? So this is our, so somehow for us the important thing was the inductive way of proving things. This was the important step somehow, and also defining it in this abstract setting. But the condition is not really somehow okay. So this is one thing, and then comes Dobrushin. So I have only this reprint, from Schellinger Institute, the reprint of his paper, and I will show you what happens to the papers in digital form after, only 10 years. This is, somehow this was certainly not there in the original paper. This is something that Adobe did, somehow you just have a new version of Adobe and it turns, brackets in the opposite, so it's, somehow. But, what I wanted to show here is somehow, in spite of the beauty of his paper, also, somehow the inequality sounds to going in opposite directions. somehow.
And so he has another name. What I call a vertex and you call a polymer, he calls an animal.
Animal, yes, and gangs, and so yeah. but what was somehow unpleasant in his thing was that the second condition of the cluster expansion I was showing, the sum over all clusters that somehow touch some point or something like that, is finite, was not present there. What he was somehow saying is that essentially the coefficients, these are our CNs, the coefficients are small, there should be, so R is smaller than something, okay? But then if you want to prove that sum over this of the series is finite overall, then you have to still do the work. I mean, you have coefficients, but you have these clusters, and you have to compute how many clusters of given size you have and all this. So once you wanted to use this was somehow nightmare. So I just want to point that it's really important to have this second part of the expansion. Okay, and this is really all what I wanted to say.
Thank you very much. Any questions? In your article, you were mentioning the Mobius formalism was introduced in it goes back to 8. Is that Rota's paper?
We say was later go back to 8. Aha, what is 8? I will look. I will tell you. I don't know. Probably not. I don't know. Mach is 9. So okay, what is?
So Roman, I just wanted to say in your favor that even though that go back one slide. Yeah. So even though this Möbius condition looks ugly, the point is the convergence of the Mayer expansion and the bounds on the Mayer expansion can be separated from getting the explicit formula for the CNs, because as you saw in my talk, it's very easy to get the explicit formula for the CNs as a formal power series. So combine that with any proof you like.
Yeah. Sure.
And you immediately have.
So immediately, I was for many years I was using our theorem, and how I was using it, I was simply, saying that this phi tc they equal sum over all CNs that have support C. This C is exactly Vn. So phi tc is exactly in this language we are using here. Phi tc is sum over all Cn Wn over n such that Vn equals C. Yeah, you simply group all the terms that have the certain size of Vn or certain set Vn. You group them into one group and you resum, and this must be exactly the same formula, because this is Möbius formula gives you unique solution, and that this is true, in this sense and also in that sense. So
I think we should stop because we have one more talk and 3 presentations of poster without any break. So I think we should stop. So thank you.